Hello, hello. Good afternoon, David. Hello. Good afternoon, Jamalette. All right, we are rolling. Good afternoon, Chloe. Good afternoon, Gianna.
Good afternoon.
Oh, hello. Oh, I got a good, wow. All right. Good afternoon. All right. That is video. That is a million points. That is like awesome. Hold on, I'm just trying to get the board back here. Okay, that I totally saw that. Believe me. Oh, and then she evolved back into IceQ or de-evolved. Okay, so good afternoon, David. Good afternoon, Amy. Tanina, good afternoon, Sophia. Oh, I missed you, Sophia. I'm sorry. Good afternoon, Jamalette. Good afternoon, Brianna. Good afternoon, Jasmine. Good afternoon, Chloe. Good afternoon, Gianna. I said good afternoon, Brooke. Good afternoon, Samuel. Book 2. Good afternoon, or 1. Good afternoon, Diana. Good afternoon, Abdel. Here comes Stephen. All right. All right. Continuing, someone said in the other class that I'm apologizing too much, so I'm going to stop. I'm just going to continue to point out that the exams are continuing to drop back too slowly for anybody's comfort, but as quickly as, so again, if you have gotten one back, terrific. If you want to discuss it, terrific. If you haven't gotten one back, that reflects nothing about you personally, except perhaps like the first initial of your first name or something. Good afternoon, Jaylyn. And so I apologize again. They'll just continue to keep back. And if when you finally get your score, if all of a sudden you think there is a catastrophe, I would imagine that there isn't, but we can absolutely discuss and prevent all catastrophes before the final. Okay, and I just lost and good afternoon, Stephen. And I'm bringing the board back. Hang on a second. So we're going to move on in material today. Again, for these final weeks, I'm just catching up and you're catching up. And it's probably more necessary. We're probably more worried about me catching up than you. Hold on. And the board is coming back. What we're going to get to today is we're going to continue with this business of electrostatic fields and electrostatic field lines, particularly. So last time we sort of introduced the idea of an electrostatic field line diagram. You looked at some. I want to you looked at some. You hopefully have now a sense of what it is you're looking at when you look at an electrostatic field diagram, field line diagram. You hopefully have a sense of how to interpret the information. Again, the ultimate information to be gleaned from an electrostatic field line diagram is magnitude and direction of field at any given location in space, right? Again, that's what these diagrams are connoting. I mean, what they're representing precisely is for any given location in space that you investigate, what is the strength and what is the direction of the electrostatic field at that point. The electrostatic field due to some source of field that is invariably depicted somewhere in the diagram. So that's how to read the diagram. I want to quickly now, someone quickly give you the rules of how to create a diagram. They look very intimidating. Well, to me, they look very intimidating. When I first saw them, they look intricate and beautiful and hopefully possibly somewhat clear, but they do look very intricate. And it looks like something that you would need a computer to make. Certainly you want a computer to render them as precisely as possible, but to actually create a field line diagram, you can do it by hand, and that's of course the way they were done originally. You don't need in advance a knowledge of exactly what the field is doing where in order to create the diagram. It's the other way around. These diagrams are not just rough sketches or rough depictions. These diagrams are computational tools like vectors or graphs, or free body diagrams, so much so that the idea behind a field line diagram is if you follow the rules governing the creation of a field line diagram, if you just follow the rules, then given a certain situation, you will end up drawing a diagram freehand and finding out from what you drew what the field is doing. That is the point of them. Again, like vectors, if you draw it correctly, it conveys information that you then use for calculation and prediction, as opposed to the other way around. As opposed to you need the information first, and then you're just sketching some sort of rough idea of that information. Therefore, they're super important. Even though we won't have time for you to draw 1,000,000 of them on your own or anything like that, I want to now turn the page and give you the rules for drawing a field line diagram, again, so that you understand really, if nothing else, understanding these rules will make it easier to read them. And hopefully give you a more precise sense of exactly what it is they're conveying about space and how. So I'm going to turn the page right now and I'm going to give you a set of rules underlying the construction of electrostatic field line diagrams. Here we go. Pause for a second. Let me just change the view of the screen. Pardon me. But again, obviously, as always, put questions in the chat. Okay, who's this? Hello, Sarah. Okay. Okay. The rule number one for creating a field line diagram is choose and maintain a scaling factor For example, oh, someone else is here, Samuel's here. You're going to choose and maintain a scaling factor. For example, 8 field lines per each coulomb of source charge. Okay, so the number 8 is an example, but other than that, this is precisely what I do mean by a scaling factor. I mean that and again, this is if you're doing it freehand, you might choose a number such as 8. If you were rendering a field line diagram in a computer, you would probably choose a scaling factor that's far more intricate, such as 1/4 pi epsilon naught. You know, that like you might say something like, I'm going to draw 8.99 times 10 to the 9th lines for every coulomb of charge, right? Because computers can do, I mean, that's a lot of lines, but that's also a lot of charge. So the more advanced your technology, the more intricate and precise perhaps your scaling factor can be. But the idea behind the scaling factor is, you're going to choose a scaling factor like this, and then you're going to obey it consistently and symmetrically. So what I mean by this is, if you go back to our original case of the field line diagram from a positive point source of charge, right? If you just had a dot of charge somewhere in the lab or somewhere in deep outer space, and there goes my board as usual, pardon me. If you just had a dot of charge, you know, the field lines from, and I hope you're getting accustomed to this claim that I'm about to make, from one point of charge, the field line diagram should be increasingly set in your mind. It's a bunch of lines radiating out in all directions symmetrically from that point, right? And if it were a point of if it were a point source of negative charge, it would be a bunch of lines radiating in symmetrically. Okay, now, remember that what we're doing in the drawing is we're drawing a representative sample of lines. The idea behind the picture, the idea behind fields is that there are lines everywhere in space, and we're just drawing enough of them. I'm trying to fix the board to get to see what the pattern is. Okay, so if you just drew, what is going on with the board? Okay, if you represent a proton in the middle of the screen, just a dot, and you realize that its field lines are pushing out in all directions, I'm saying before you even draw that dot, make a decision in your mind, say something like, okay, if that's 1 coulomb of charge, I'm going to draw 8 lines. If it's 2 coulombs of charge, I'll draw 16 lines, et cetera, et cetera. And so you make that decision, and then you go in and you draw those lines symmetrically. By the way, that's why I'm picking the number 8. It's a reasonable number, like we've been doing on the board, like an asterisk, 1 up, 1 down, 1 left, 1 right, and then 4 going diagonally at 45 degrees each, right? So when I draw those 8 lines as symmetrically as possible coming out of that 1 dot, it's now a rule that I'm going to follow throughout. If it turns out that I'm doing the field lines from a dipole or something like that, if it turns out there's another charge somewhere in the page, that's acting as a source of field, if that other charge is equal, if this is strictly a dipole, then there'll be 8 lines going into that other charge. If the other charge is twice as strong in magnitude, then I'll have 16 lines going in there. I'm just saying from here on in, for each bit of charge that's causing field, you follow a consistent scale to determine how many lines to draw, and then you just arrange them as symmetrically as possible. Okay, so that's rule number 1. So then you start drawing. Okay, rule number 2. And I think I mentioned this rule yesterday or Monday. Every field line, so here's rule number 2. Every field line must either start at a positive source or come in from infinity, which is a weird thing to say. I'll elaborate in a minute, but it is the case. So every field line, it either starts at a positive or, in effect, it doesn't start at all. It's just understood to come in from ever. And similarly, rule number 3, every field line must either, you can imagine where this is going, end at a negative source, which we can therefore also call a sink, or go off to infinity. Okay, now those are rules. Now I'm going to pause on this for a second and say, when I still remember when I first heard those rules or something to that effect, when I was a sophomore in college and heard something about this. And I remember thinking, yeah, okay. First of all, I thought, like, what do you mean go off to infinity or come in from infinity? Like, what are you even talking about? I thought we were drawing these lines on a piece of paper. What is infinity? But then when I understood they basically meant by infinity, they mean off the edge of the page. They mean just assume it's going on forever, which is what they mean. Like, they mean if a field line doesn't land at a clear negative somewhere on the page, then we assume it's going on forever. Okay, that is true. That is what they mean. But at the time, I thought to myself, well, yeah, okay, as opposed to what? Like, what are you even saying here? It either starts at a positive or comes in from infinity. Like, that covers a lot of ground. What else could it possibly do? What they were saying that I didn't realize at the time is they were saying, as opposed to lines starting or stopping spontaneously in the middle of the page, or starting, in other words, they're saying remember, this is all supposed to be a representation. These drawings are a representation of what's actually happening in space. So what we're saying with this rule is field lines do not start or stop spontaneously anywhere in space. They are neither created nor destroyed, so to speak, just at random points. The only thing that can create a field line is positive charge. And the only thing that can, so to speak, absorb or receive a field line is negative charge. That's what we're saying. They don't. And so another way to put this, okay, so what we're making a claim about space and saying field lines do not spontaneously begin or end. And and of course, again, I have to remind you, the only reason I care about all these rules about how to draw them is I'm hoping you'll see that in the rules for how to draw these lines, we're really telling ourselves what we believe about fields in space. But another way to put this whole rule, this pair of rules, rule 2 and 3, is what we're saying here really is field lines are not vectors. They're built from vectors. It is true that at any given point on the page, when you look at the collection of lines you see on the page, that point on the page is telling you about a vector that you could imagine to be there. What you're inferring from these lines anywhere on the page is a magnitude and a direction that absolutely could be represented by a single vector, could be. And again, if you remember, all these lines that we're drawing came originally, they were constructed originally from a whole bunch of vectors that were on the page. Like we are still talking about vector quantities here, but the lines are a new representation. They are a smoother, different kind of representation that are rooted in vectors, but they are not vectors. Very specifically, what I really mean when I say that field lines are not vectors is I mean field lines don't have length as such, or when they do, their length doesn't represent anything. They either have an infinite length, or if they have a finite length, it's because they're coming from one positive and landing on a negative. And so whatever their length is just a space between those two charges. Their length does not represent magnitude the way that a length of a finite arrow, known as a vector, represents magnitude, right? Okay, so this is rule number 2 and 3 basically is saying field lines, they just go on and on, or they do not have tips. They have tips, but they don't have tails. And last corollary to that too, you may notice, it took me a really long time to notice, you notice field lines do have arrows. They certainly have direction, right? That's a big part of the point. But you notice when you start looking at all these diagrams on Google Images or whatever, you notice that the arrows for field lines are always just like right in the middle of the line. Frankly, I missed that for decades. But if you look at the pictures, the arrows are arrows, but they're not tips. They're not at the edge of the lines. They're in the middle. It's exactly for this reason that is the case, where the lines express direction, but they don't express termination. So just note, arrows of field lines are always just in the middle. You could almost call that another rule if you like, are in the middle. So the lines go on and on forever if they don't land on a negative. Okay, that's rule 2 and 3. Okay, rule 4. Because of this, I mean, then it follows the whole point of the lines, what we said 2 days ago, the orientation sorry, hold on. So at a point, on the page, direction of field is represented, or is interpreted, is understood, is read, is represented by the tangent to the field line at that point, right? So if you look at any point, so if you look at a page, and by the way, while I'm writing all this or while you're writing, if you feel free to be maybe looking at Google images at any of these field line diagrams that we were looking at Monday. Any one will just make clear what I'm talking about here, right? Hopefully. So you pick any point on the page where there's field lines, wherever you're looking at, you look at the nearest field line, the tangent to that field line, right? In other words, the instantaneous slope of the field line, the way the field line is curving at that point, which is best visualized by the slope of the line tangent to the field line. The tangent to the field line at that point is the direction of the field at that point. And no, why? And you might be thinking, depending on who you are, might be thinking, oh my God, where did tangent come into this? Like, why is he suddenly talking about tangent lines? Where did that? Well, the reason I'm suddenly talking about tangent lines is because the field lines can be curved, and they usually are curved, right? So, but to be curved means to be changing your slope continuously. So if something is changing its slope continuously, it means it's changing its direction continuously. So if we want to know direction at a point, that's like knowing derivative, right? I mean, we need to visualize a line tangent to the curve at that point, and the slope of that tangent line is the direction of the field line at that point. So first of all, direction of electrostatic field is represented by slope of the line tangent to a field line at that point. So that's direction. And by the way, again, if all of that is going through in one ear, not the other, I'm just saying the curvature of the line represents the direction of the field at a certain point, as you would expect. That's why there's arrows on the field line. But then similarly, because these are not vectors, magnitude of electrostatic field is represented by, maybe I'm going to pause and ask you. Okay, I'm going to pause here. So buckle your seatbelts. I'm about to ask you. I'm going to wait for there to be 3 answers in the chat. Now, we said the answer to this on Monday. This is not a trick question, but I want to know if you remember from Monday, or if you can infer from what I'm saying here. When you look at those field line pictures, you look at a certain place on the page that has a bunch of field lines on it. How can you tell the magnitude of field? How can you read the strength of the field from the lines you're seeing on the page? Now, again, this is not a trick question. We said the answer Monday, but I just want to make sure we're clear. And again, in contrast, if we were looking at vectors, if we were looking at a vector field diagram, then at any given point, the length of the vector would show us the magnitude of the field, right? That was the old way, but that's what we're getting rid of now. We don't have vector lengths anymore. So if you're looking at a point on the page and you want to know the magnitude, the strength, the intensity of the electrostatic field at that point, how could you read it from the field line diagram? What aspect of the lines are you looking at in order to infer magnitude of field? And I'm looking for words here, not numbers, but I'm going to pause. I'm going to also change it. So I'm waiting for answers in the chat. Again, the question is how, what aspect of a field line diagram indicates good. I'm going to finish the question, but I just saw one answer and it's right. And I'm totally psyched, but I'm going to wait for 2 more. Yes. The question was, what aspect of field line diagram indicates magnitude of field? There's 2 people. Hold on. Okay, there's 2 people in the chat. I'm totally psyched. First of all, that's 2 people in the chat. That's great. One person is saying a totally right answer. I mean, I can't. One person is giving me an answer that is the correct answer about direction. One person is definitely telling me something correct about direction. But what I'm asking right now is magnitude. I'm asking, how can you tell how strong the field is if you look at a field line diagram? So 2 people are definitely with me. I mean, you're definitely hearing the question. I appreciate that. But I think one of you is sort of answering about direction, and I'm asking about magnitude, quantity, strength. So I'm going to wait for, this is great. 2 people are with me. I'm going to wait for one more person to say, even if, I don't care if the answers are right or wrong. And obviously, you see I'm catching up with the points. that I owe you guys too. They're also slowly coming back. They will all be accounted for before the final or before the end. But I'm waiting for one other person in the chat to answer to attempt to communicate. The question is, what aspect of a field line diagram indicates strength of field? And if I can't get an answer, can I get electronic show of hands of who even hears the question? Do we hear the question? Oh my God. That's yes. Okay. Thank you, Jalen. Thank you, Samuel. Thank you, Diana. Thank you, Jamalette. Thank you, Amy. Thank you, Brianna. Awesome. Okay. So does anybody want to take a stab at this? Thank you, Chloe. Thank you, Chloe. I said someone else too. Thank you, guys. But so do you understand the question? And maybe I will switch screens in a second and show you a field line diagram again, but you do want to know this is important. Nothing else can happen without us building on this concept. I need one more person. I'm going to cry. Don't make a grown man cry. Okay, I'm going to switch the screen and show you a field line picture. Hang on one second. Wait, you know what? Maybe, all right, hold on a second. What, if you want to answer in the chat this instead, what aspect of a vector, like let's make sure we're on the same page here. Answer in the chat, what aspect of a vector, of an arrow, indicates the magnitude of vector quantity? Oh, and Samuel, is that a question or are you just keeping your hand up from before? If you're, that's cool if you're. So I'm changing the question. Yeah, wait, I'm not going to, oh. No, I don't see. I'm not going to move on until I get something with this. Look, back to physics 203. You have a vector. You have an arrow. The way it's pointing, its tip or tail orientation indicates the direction of the vector quantity. What aspect of the arrow indicates the magnitude of the vector quantity? And this is, I'm not going to move on until I get an answer to this. This is not a trick question. You know the answer to this. You either are thinking it's harder than it is, or I'm not expressing it well, or I'm losing everybody. How can you tell from a vector arrow how big? I almost just gave it away accidentally by saying that. How can you tell the size of a vector quantity from looking at the arrow? Oh my goodness, it is the end of the year here. Okay, raise your hand. Oh, wait. Okay, cool. Okay, first of all, someone in the direct chat did just answer my question about the arrow. Thank goodness. You were about to see. Cool, 2 people just did. Okay, and you're both right. And I want to say, so 2 people just correctly said, so, okay, we're back on the same page. We're back in business. 2 people just clarified that with a vector arrow, it's the length of the arrow that indicates the magnitude of the vector quantity, right? I mean, that's not supposed to be a trick question. I'm just trying to set up a contrast here. So 2 people, oh, nice, sweet. So 2 people, or 3 people, sorry, 3 people just got that right. Thank you very much. I also would like to point out that one of the people that just got that right is one of the people that from before might have misunderstood my question or something like that. So that's total redemption. They're totally back in business. You're all back in business. So now here's the contrast. If with an arrow, the length of the arrow indicates or represents the magnitude of the vector quantity, then now with field line pictures, you see, field line pictures are a major advancement. They're a very important representation, but they are a change. Field line pictures, field line diagrams get rid of the arrows. We don't have arrows of finite size anymore. So we no longer have the ability to represent magnitude through the simple concept of length. Like we lose that in a field line diagram. So something else must take its place. There's some other aspect of the field line diagram. Like if you're looking at a certain, and look, flip to Google Images in a minute, or I will. If you look at certain regions of a field line diagram, you'll see a certain quality to the lines that even unconsciously probably makes you think of the field as stronger there. And then in other regions, you see a different quality of the lines that makes you think the field is weaker. And it's not just you, and it's not just your emotional response. It is the actual technique of the representation. So, and 2 people have answered this correctly so far, but I'm looking for, I think 2 people. I'm looking for one more person. I want to know, when you look at a field line diagram, what is it about the lines that tells you how strong the field is? So I'm going to wait. And I'm going to wait until I get one more response, because we really do need it. Oh, well, good. All right. There is something in the chat. Someone just put something in the chat, which is good and totally shows that they're listening to me, or that they're with me. And they totally understand the question. Wait, okay. So I'm getting two answers in the chat. They both show a recognition of my question, but they're both a little bit misguided as answers. Hang on. All right. So I'm going to switch screens for a second and show you what I'm talking about. These are good answers. I mean, I have 3 people in the chat now. I'm totally seeing your answers. I'm not going to read them out loud maybe yet. You're on the right track, but maybe I'm not making the question totally clear. Hang on. I'm going to switch. But you do, and I think it's no more complicated than what you guys are thinking. Hold on. Let me just hang on. Bear with me for a second. Okay. Bear with me. I'm just pulling up a picture here. It is coming, or is it? Same picture as yesterday. Okay. Okay. The picture is loading. I'm gonna. Okay. I don't know why it's taking so long to load. Why is it taking so long? You can see. Oh well, you can faintly see it there. It should be coming. I don't know why suddenly my computer is running on low octane fuel, but I think you can faintly see those images that will be fading in. Well, can I get this? Can you electronically raise your hand if you can at least see the images that are on my screen? Sort of, thank you. They're sort of limping in. This is crazy. This is like, should I check my modem line? Like, what is going on here? Okay. Okay, so look at those pictures. So thank you. I see the hands. Thank you, Jasmine, and thank you, Samuel, and thank you, Amy. And there was, I think, Jada. Okay, so someday, there we go. Okay, so there's the pictures. So these are various different field line pictures. Again, why the different pictures? Because they're the field lines being produced by different arrangements of source charge. Like one is A positive and A negative, equal in magnitude. One is 2 positives, equal in magnitude. One is a positive and negative, but the positive is a lot. But the negative is a lot. Sorry, the positive is a lot stronger than the negative, right? And by the way, you see when I'm saying that they follow that scaling factor thing, like the more well, so here's the point. Go back to my first rule about scaling. We said that for any given number of coulombs of source charge, we draw a particular and consistent number of lines. So the stronger the charge, the more the lines are that are coming out from it. We've already, in effect, said that in our scaling rule. So if you then look at these pictures, what I'm getting at is if you look at these pictures, it's the regions that have more lines per unit area on the page that are representing stronger field. And I'm gonna say that again. Well, I'm gonna say it again, then we're gonna write it down, but I want to make sure you understand. I'm saying it's like I'm saying that these lines on the page, they might look like they have length. Like one person put in the chat that the lines that he or she were looking at appeared to have length. So does it have something to do with length? I'm saying, I'm sort of trying to very forcefully say, these lines don't actually have length in any meaningful sense. These lines, all of these lines start at positive and land at negative. So they're just as long as they need to be in order to make that journey from positive to negative. Or if they don't land at a negative, or if they don't start at a positive, the idea is that they're coming in from and going out to infinity. Like let me make that very clear. Like Look at diagram B. It looks like you have a whole bunch of lines that are all, forming this square, that they're all like bending. So yeah, you could put a ruler to each of those lines and say, oh, that line is 5 centimeters long. But it would be a mistake to take those 5 centimeters seriously as meaning anything, because the idea behind all of those lines in picture B is, since they're not hitting a negative, they're understood to go on forever. In fact, that's why in those cases, like the arrows are being put at the ends. They're saying, please assume that we just ran out of room on the page. These lines are understood to extend eternally. Okay. And the lines that, and same thing in diagram A, the lines that are coming into the negative that don't seem to have any origin point, they're coming in from infinity. So you can't infer anything from the length of these lines about magnitude. What you can see, though, is that in certain regions of the page, lines are closer together. They're denser in certain regions of the page than in others. Wherever the lines are denser, that indicates stronger field. And it's not just a loose, approximate, impressionistic thing. It is that we've already established a scaling factor in rule 1. So we can actually, if we're really rendering these on a computer and looking at them on a computer as we right now are, we can trust that if there's twice as many lines per square centimeter on the page in the middle of this diagram A, if there's twice as many lines per square centimeter in diagram A as in the middle of diagram A as there are at the edge of diagram A, if there's twice as many lines per square centimeter, then we in fact precisely believe or understand or compute that the field strength is twice as many newtons per coulomb in the middle of the page as it is at the edge. Like it's a mathematical tool. And the upshot of the mathematical tool is density of lines per, well, we're going to write this down right now. I'm going to stop the share. Stop the share. I'm saying, so what I'm saying, then I'm going to pause and make sure you're with me. I'm saying magnitude of field is represented by density of lines per unit area on page. So magnitude of field, I'm just going to just so the magnitude of field in some region of space is indicated by density of field lines per unit area on the page, on the part of the page representing that part of space. Okay, I'm going to put, okay, bottom line, magnitude is density per area when it comes to field line pictures. I'm going to put, can you please honestly put up your electronic hands if you're with me on this, if you get it now. Cool. Okay, thank you, Jamila. Thank you, Amy. Thank you, Diana. Thank you, Jaylyn. Thank you, Chloe. Thank you, Jasmine. Thank you, Olsmail. You liar, Olsmail. You just walked in. Oh, no, I didn't. Okay, thank you, Jaylyn. I didn't, did I just say liar? I meant liar like the instrument, like the Greek instrument, like a flute, like that kind of liar. That's what I mean. Oh, thank you, direct chat person. I see it. Oh God, 2 direct. Okay, 1. Yeah, no, I did. Oh, she went. Okay. No, thank you, direct chat person. I'm glad. Cool. I appreciate that. Okay. And I know that people were putting things in the direct chat that I hope that, I mean, it was good. Okay. If we're good, we're good. So that's rule number 4. We're almost there. Rule number 5. Field lines. So now if you picture in your mind the pictures we were just looking at, like, they get intricate. And again, please understand those pictures we were just looking at, you understand, or you see, the pictures get increasingly intricate as the distribution of source charge gets increasingly intricate, right? If you just have one point of charge, you have a fairly simple diagram. If you have 2 points of charge, you have a slightly less simple diagram. If you have 2 points of charge that are unequal in magnitude, the diagram gets even more complex. You can imagine what starts happening to these diagrams once you have a whole bunch of points, or better yet, more realistically yet, if you start having an actual shape of charge, if you have so many points that they're gathered together into some sort of shape, like a sphere or a cylinder or a plate, right? Then we really start having interesting field line diagrams. And that's the goal of all this ultimately, is to be able to depict what is happening in space over here due to some collection or distribution of continuous source charge over here. That's the idea of all of this, is what impact does charge over here have on space over there? That's the point of all this. So anyway, rule number 5 is field lines can and do bend, curve, so field lines can totally bend. Again, they're not vectors, right? You saw in those pictures, field lines can be very, very curvy. But they, first of all, they always bend continuously. Like they don't make right angles. They don't suddenly what's the word I'm looking for? They don't turn corners. They bend, and they bend smoothly, continuously. Like all the changes in the direction of the lines are gradual and predictable, continuous, right? So they do bend and curve, but always continuously, i.e. smoothly. And furthermore, even though field lines can bend, field lines never cross. I don't know if you noticed that when you look at those pictures, but so they never cross. And why? Each field line because the reason the field lines never cross is that each field line is already a representation of net electrostatic effect. Let's tell you what I mean. By definition, the field is the net electrostatic force per charge, right? Like that entire long problem we did last Wednesday, where we added up the two, we wanted to know the field over here at the origin due to 2 point sources over here somewhere in the first quadrant of a coordinate system. So what we did is we said one of those point charges created a vector. It deposited a vector over here at the origin. The other point source deposited a vector over here at the origin. So we had 2 vectors being deposited at the origin from 2 separate point sources, but we went through all this mathematical work to add the 2 vectors together and get one final vector at whose tail was at the origin, and we called that final vector the electrostatic field vector. Like we did all that work to add 2 vectors together, get the superposition of those 2 vectors, and call that final answer the field. The field is, by definition, the net effect of everything that's causing it. The reason we need this whole field line diagram representation and all this is because we're ultimately trying to look at really complicated situations where the field is created by a whole bunch of different sources, each source contributing its own vector to a given point in space. So the field is the result at the end of the day of a bunch of vectors being added together to create one big vector at every point in space, right? So the field is the superposition of a bunch of lines. If you ever had two lines crossing when you were trying to draw a field line diagram, if you ever had two lines crossing because you thought, well, one line is coming from over here and the other line's coming from over here, when you draw the two lines crossing, what that just means is you're not done drawing yet. Because once you see those two lines, one coming from over here, one coming over here, your job is then to do the vector sum and get the one line that represents the addition of the both. So when you're done drawing a field line picture, at the end of the day, when you look at a field line picture on Google Images, it can't have any crossing lines because it means it's a rough draft of the, that would mean it's the rough draft of the picture, not the picture. The picture is the final result. Lines cannot cross. Okay, I can't say it any better than that. Well, maybe I can, but so that's line number 6. I mean, that's rule number 5. And then finally, rule number 6, I believe. Yeah. So then line number 6 is a field line diagram will be the simplest, smoothest. Oh, sorry, wait. There's, well, it was one of the things I want. Sorry, there's one other rule I have to say before that. My bad, my bad. Field line diagrams a field line diagram will necessarily, if you do this correctly, will, I'll say should grow increasingly simple, symmetric, uniform, as we look farther and farther from the source charge. Okay, what it says is, so a field line diagram should grow increasingly simple or symmetric or uniform as we look farther and farther from the source charge. And I'm talking about, again, on everything I'm saying here is about a piece of paper or a computer screen where we're drawing a diagram. This is all about how you understand the diagram. Again, I wouldn't care just about some diagram, except for the fact that this diagram is supposed to rigorously represent something that's actually happening in space. So part of the thing of the diagram is that, and maybe I'll screen share again here. If you look at these pictures on the screen right now, they can get pretty intricate. And I mean, each one is as intricate as the thing that's causing it. The simpler the source charge arrangement, the simpler the picture. But now, no matter how simple or complicated the arrangement of source charge is. What you notice if you look at these pictures is as your eye gets farther and farther away from the source, the pluses and the minuses, the charge that's making the lines, as your eye goes farther and farther away from that, the picture gets less and less complicated, or that, at least that's what I'm claiming. The lines start falling into a simpler and simpler pattern. And if you went far enough away from this, you should see the lines getting approximately, just a bunch of parallel lines. Because the idea is that field gets weaker and weaker as we get farther and farther from the thing causing it. The complexity of these pictures has to do with how differently each bit of charge is contributing to the overall field. So like if you have one positive, or if you have a positive over here and it's pushing everything out away from it, then you have another positive over here and it's pushing everything out away from it. Then in between the two pushes, you have these conflicts. You have a push to the left and a push to the right. So the lines start getting funny. But the farther and farther away you get from either of those charge, the less and less you're feeling the effect of either of those charges. So the farther and farther away you get, not only are you going to feel the less and less will you feel the effect of each individual charge, but you'll therefore feel less and less the effect of any conflict or any conflict between the charges. Like they're all, as you get farther and farther away, each charge is increasingly doing the same thing to you, which is almost nothing. Right? So as you get really, really far away in space from a whole bunch of charges, you feel essentially the smoothness of space. And that should be captured in these pictures. As you get farther and farther to the edge of a piece of paper or a computer screen on which one of these pictures appears, you should see lines that are doing more or less the same thing, more or less parallel with one another. Okay. That and by the way, why am I saying parallel? Because again, remember, the density of lines indicates the strength of field. Parallel lines, by definition of parallel, mean lines that are not getting less or more dense anywhere, right? If they're parallel, they're always the same density. So parallel lines indicate uniform or constant field. So when we get farther to the edge of a page, we should be seeing something closer to a uniform field. I'm going to switch back screens in a second. I hope this is sort of clear. But by the way, I'm sorry, Amy, do you have a question, or is just your hand from before, or did I miss you and you have a question? Oh, okay. All right, cool. But thank you. She pays a lot of attention. You see how fast she just responded? See, that's called paying attention. I'm just saying. Okay, I'm going back to, wait, but her hand didn't go away on the, wait, that's so weird. Why did it not go away? Well, anyway, okay, I'm going to go back to, because my board is frozen again, as usual. Okay, I'm going back. Well, I'm going to try to go back. Hang on. Okay. Okay, we got 20 minutes. Hello, go. There we go. Okay, so that's rule 6. Finally, rule 7. Okay, so bottom, if I had my way, we could spend the next like 5 months drawing field line diagrams together, practicing. Obviously, we're not going to do that. We'll practice a little bit. There will be There's often some little bit of this on the final, but the bottom line is this. When you sit and drawing field line, look, it looks really intimidating to draw these pictures. It's actually a lot less challenging than it looks. And whether you find it challenging or not, what I'm really trying to argue is that if you sat down with a piece of paper and someone said, okay, imagine a positive point charge over here and of 1 coulomb and a negative point charge over here of -3 coulombs, draw the field line diagram for that situation. If you sat down and followed these rules, the ultimate thing I'm trying to say is, if someone said, draw the field line diagram of this situation so that we could infer magnitude and direction of field for every point in space in this situation, if someone said that to me, okay, what would go through my mind first would be like, well, I don't know what the magnitude and direction of the field would be at every point in space. I can't draw that picture. Like, I mean, I have no idea how to draw that picture. If that picture is supposed to show magnitude and direction of field at every point in space, I don't know how that would be distributed. I don't know how to draw the picture. But what I'm saying here is, if you sit down and just follow these rules, if you sit down and say, okay, I'm going to pick a scaling factor, I'm going to say for each coulomb of charge, there's 8 lines that are going to be symmetric. Oh, 1 second. Sorry. Oh, wait. Sorry. Oh, okay. Oh, gosh, right. Yes, thank you for telling me. Yes. Oh my God, that's today. Wow. Yes. Yes, go over and okay. Yes, everybody. I almost forgot about the Prism thing, which I wish I were there for that. But please stop by and say hello to Justin Colon and Alyssa Reynolds, please, everybody. But yes, Prism. Okay. Sorry. If I sit down and I follow the rules and I say, okay, for every 1 coulomb of positive charge, I'm going to draw 8 lines. I'm going to draw them symmetrically, which therefore means for every 2 coulombs, I'm going to draw 16 lines, or every 3 coulombs, I'm going to draw 24 lines, etc. If I sit down, make that decision, and then I look at the page and I'm like, okay, there's a positive charge over there, so I'm going to start drawing lines coming out of it. Oh, there's a negative charge over there. I'm going to start drawing lines coming into it. Oh, there's 8 lines coming out of that positive. There's 4 lines going into that negative. Okay, the 4 lines that went into the negative, I'm going to hook them up to the lines coming out of the positive. Oh, there's 4 left over. I guess they go off to infinity, right? If I just start following these rules and say, I'm going to draw this from the positive, I'm going to draw these to the negative, I'm going to draw them, I'm going to arrange them symmetrically, I'm going to have any lines that don't have a match, I'm going to have them go off to infinity or come in from infinity. I'm going to let my lines curve as much as they need to, but always smoothly and continuously. I'm never going to cross any of my lines, and I'm going to make it look smoother and smoother as I go out to the edges of the paper. If I literally just follow those rules and every single time make a decision about lines that conforms to all those rules, but is always the simplest, most symmetric, most smooth decision I can make for each line that I add, or how to make it go from over here to over there, then I will automatically create the correct field line diagram. Like, that's what's sort of magical about this. If I just follow those rules and draw the simplest, smoothest picture that I can, that accounts for all of the lines according to these rules, then I will have the picture. And it will, I mean, it might not be perfect because like I might be a spaz, but I will have the correct picture. And then that picture will tell me magnitude and direction of field at every point in space, much the same way that if you just follow the rules for creating a free body diagram, then when you're done, then you have all the magnitude and directions of all the forces acting on a point of mass, right? So the picture is actually ending up being a quantitative computational tool that does work for you. You don't do the work to create it. Once you get used to following these rules, it does the work for you. Okay. So that's a bottom line behind field line pictures. Now we have 15 minutes. I mean, I know some people are going to Prism, and again, thank you for warning me. But now what do we do with all this? Like, what's the point of all these field lines and everything? Okay, so that's done. That's the end of it. So now we're going to turn the page. So what do we do with these field lines? We're going to we use them to help us understand and introduce a concept of electrostatic flux. Okay, we're going to introduce this idea now of electrostatic flux. In general, flux in physics means flow. I mean, technically, like etymologically, flux means flow. In physics, flux means stuff flowing through an area. It always means through an area. And so it means stuff pushing through or pulling through or penetrating through or flowing through an area. Specifically, in the case of electrostatic flux, what we mean when we talk about, when we measure or quantify E flux, we're talking about the number of E field lines flowing through an area. Specifically, as it said on the front board today, hold on one second. One second. Okay. Okay. Okay, sorry. All right. Okay, so this is a bit of a concept here. We're not going to get. Okay, one second. Oh, sorry. One minute. Okay, I'm going to say this. I'm going to do this. This is a bit of a rigorous notion, which we need for the next class, et cetera, et cetera. I'm going to sort of explain this backwards. I'm going to sort of explain this from the punchline backwards. Okay, so the punchline is electrostatic flux. First of all, flux is designated with a Greek capital letter phi or phi, the capital phi, and then lowercase, and then subscript e to note that we're talking about electrostatic flux here. There's other kinds of flux in physics. There's velocity flux, there's magnetostatic flux, etc. But this is electrostatic flux. Flux always means stuff through an area. But now, we express it as a double integral of dot products. It's a double integral of dot products. Now don't let the double integrals intimidate you. I mean, well, you can do whatever you want, but don't let the double integral intimidate you. It's double because it's a two-dimensional integral. In effect, it's an integral with respect to area. So secretly hidden within what it really is an integral along a width times an integral along a length. So width times length makes area. So it's a double integral because integrals, strictly speaking, are continuous sums along a particular axis, as we learned at the beginning of the course, right? So the idea behind this double integral is and remember, an integral is a continuous sum of products. The product here is electrostatic field times area. The product is field times area. The sum is representing the idea that we might have a very big area. Okay, so as I said, I'm sort of trying to do this back. So in the end of the day, flux is total amount of field lines going through a total amount of area. Yeah, if you had an area of 25 centimeters and you had two electrical field lines busting perpendicularly through that area of 25 centimeters, at the end of the day, we would say, okay, two field lines, 25 square centimeters of area. We would say two field lines times 25 square centimeters of area makes 50 lines times square centimeter. Our flux would be 50. Okay, if we added more lines, we would have more flux. If we made a bigger area, we would have more flux. So flux is not a density. Flux is not division. It's not a quotient. It's a product. It's a multiplication, right? The total number of lines you have throughout a total amount of area multiplied together gives you the total flux. And that's what it is. It's just stuff times area. That's what flux is. We're going to do stuff with it next class. I'm not going to do anything with it right now, but let me expand a little bit more about what it means. Like you might say, well, why do you have to get all fancy and have these vector symbols and these integral symbols? Why can't you just say it's field times area? Well, because I don't have to have an integral unless, or it's just like integrals always. The integral is the continuous sum. It's a procedure. It's saying, look, stand over here in this little bit of area, ask how many field lines are going through that area, multiply the two together, put it in your bag. Now take a step to the next bit of area, ask how many field lines are going through that area, multiply the two together, the number of field lines and the size of the area, put that in your bag, take another step, et cetera, et cetera. What we're saying is you're going to add up the amount of field lines times area for each little bit of area until you've added them all up and gotten your whole area and your whole total amount of flux. The reason we have to be that careful and think of it as a procedure that way is because we're taking into account the fact that some bits of area over here might have fewer lines or more lines than some bits of area over there. Right? If all bits of area all had the same number of lines going through them, then yes, we could take the E out of the integral and just say, sure, flux is number of lines times area. But if we're being rigorous and we're being mathematical and scientific and we're saying, you could have a field that varies in its strength from piece of area to piece of area, then the total amount of flux through that whole area has to be understood as an integral, and technically a double integral because it's two-dimensional, not one-dimensional. Okay, so that's why it's an integral. But again, what flux is stuff times area, specifically number of field lines times area. Why is it written like a dot product with all those vectors and everything? Because it is a dot product. Because in fact, when we're counting flux, we only want to count the component of each line that is actually perpendicular to the bit of area. That's what we really mean by flow. We mean flowing through. Now, yes, but that's what we mean by flow. I mean, the lines are actually static. I'm not saying flowing in time, but I am saying flowing in space. So to count something as flux, this counts as flux, like these lines going through my top hand count as flux. This would not count as flux at all. If you had field lines going parallel to a surface, that's not flux. And anything in between, if you have lines hitting a surface at an angle, then it's only the component of the line that is perpendicular to the area that we count as flux. And the technical way we do that is every little bit of area we regard as a vector. Now, and this is the last thing I'm going to say. This is a technicality, but it's drawn on the page here. A bit of area, a little square, it's not an arrow. It's not technically a vector at all. But it has orientation that we want to track and we want to pay attention to. So the way we do that is in our minds, we stick a little arrow coming out of any bit of area. We call that arrow the normal arrow, normal meaning perpendicular. So we stick a little flag, a little vector in our mind, sticking at right angles to any little bit of area. We call that the normal vector. And then we say, okay, the overall vector that represents this area it has a magnitude of whatever the area is, ds, infinitesimal bit of surface, right? And multiplied by a direction, whatever the direction of that arrow is. That arrow is normal to the area. And the idea behind that arrow is if you were to rotate the area, the arrow would rotate with it the exact same amount. So from now on, when we picture areas, we picture these little arrows sticking out of them. And therefore, any E field line that comes in parallel to that arrow is necessarily coming in perpendicular to the surface. So when we want to just count up the number of lines that are going perpendicular to a bunch of little surface bits, what we're counting is the dot product. We're adding up all the dot products between E field vectors and surface normal vectors. So it's right. And when those two things are parallel, it's a full-bodied product. And when they're perpendicular, it's zero product. So we're going to end with that. But that's what does all this have to do with anything? Flux is E field times area. But remember, E field itself, E field magnitude is number of lines per unit area. So this seems like a very complicated concept. I'm ending with this. I know it's 1:30, and I will end. But this concept of flux seems out of nowhere and seems very complicated. But flux is field times area. field is number of lines per unit area. So what this concept really is number of lines per unit area times area. What this concept really is the mathematical expression of number of lines. In the end of the day, when we look at our field line picture, any part of the picture, you count the number of lines, that's called the flux. Literally, the number of lines is called the flux for an electrostatic field. I'll end with that. We'll keep up next week. You keep catching up. I'll keep catching up. I thank you all deeply. And I thank you for your patience and indulgence and flexibility. Okay. Thank you. Have a great day. Thank you. Bye. Have a good day. I'm going to stop recording.